All right. It's going to be really hard to follow, Brent. I have no stories about Guatemala. But yeah, so I'm Ankush. I'm the Intrapreneur of Additive Manufacturing at Glidewell. I'm a mechanical engineer by training, but most of my background's in additive, and we at Glidewell are one of the largest dental labs in the world. We're based in Irvine, California. We serve more than half of all of the dentists in the US, and nearly all of our production happens in our Southern California facility. Now, the focus of my talk today is really about design for additive and the fact that we're usually limiting it to certain aspects of the design approach and the product development life cycle, and hoping to go beyond what. Sorry, let me just mute that. That's my bad. Yeah, hoping to go beyond what we're currently doing and rethink how we can really take advantage of additive, but also just the design approaches across the entire production floor. So generally speaking, performance and aesthetics are the core aspects that kind of go into design. That's just another way of saying function and form. That covers everything from the way it looks, colors, and light weighting, performance, mechanical properties, all of the good stuff. And once that's done, generally speaking, there's a lot of closed loops of feedback there, prototyping using additive, and then moving into production. That's when we kind of get the printing step, and there's some design for printing. So we saw some really interesting presentations this morning about unique approaches to slicing and how that can improve the parts that you're printing. But really, the reason I put printing as the word there is because that's just one step of manufacturing using additive, and one might say that's where you go from bits to atoms, but really it's just the first step. And once we're printing something and we're getting the part off the printer, really there's a good chunk of post-processing is involved, as you all know. Not just the post-processing that's specific to the additive technology that you're using, but also any other polishing, finishing, dyeing or coloring of the parts, any of that. And then there's also QC. QC can be as involved as 3D optical scanning or CT scanning, or just something as simple as a visual inspection by a trained technician. And in addition to those steps that come in after the printing step, there's also everything that happens in between. So each of those red arrows represent part flow, right? The parts are moving from one step to the other across the production floor, and again, each of these are opportunities and or potential problems based on what you're printing and how we're approaching that. So the first chunk of it is really where most of design for additive gets focused, and most of that's in the product development stage, excuse me. And we're really neglecting the needs of the rest of the production workflow and what the rest of the floor needs. And so I wanted to touch on one example today, and really this is just one example, but the idea is to kind of take this approach to rethink how we can best make the most of design approaches. So the example I wanted to talk today about is 3D printed sports guards. So mouth guards for athletic use. Generally speaking, most of the dental industry makes these in the following way today. So we start off with a 3D printed model. So that's the beige colored unfortunate jaw that you see on the left. Usually that's either 3D printed, or it can just be something as simple as a technician pouring stone into an impression that we get. So the way we get that data from the dentist is usually one of those magic wands that they put in your mouth and we get the 3D scan, or it's one of those impressions that you have to bite into and wait for 2 minutes while you're gagging and just salivating all over the place. It's not a fun process. So once we have that data, we're then 3D printing the model, and that model goes into a thermoforming machine. So That's just a traditional, suck down machine. We have a blank of the polymer that's going to be the final material of the guard, loaded into the machine. It gets heated up, gets pressed onto the model, wait for it to cool down. A technician then takes that off. That's what that looks like, and they're trimming it off. They're making sure the edges are smooth enough, and any other adjustments to be made based on how that fits over the model or anything else that the dentist may have requested. Once that's done, we're polishing that guard, and again, this can take anywhere between, I'd say 1 to 4 minutes, depending on how thick the guard is. Usually the thickness is either a function of the blank itself or just the number of blanks that you use, depending on what the dentist requests. So once that polishing step's done, then you have your guard and you ship it out. So what if we wanted to use additive to kind of improve this workflow and digitize it a little bit? Well, most of the dental world, as some of you may be aware, is really printing using photopolymers. And that makes up a good chunk of not just dental printing, but also a sizable chunk of the photopolymer market is really that dental industry. So let's look at that. So if we're printing the guard directly, then we no longer need the model. So we've eliminated one step. We have the 3D file, which is a design file. And again, the advantage here is that since we're starting off digitally in CAD and we're staying in the digital environment, that can be automated and kind of systematized to the best of our ability. We're then moving that to the printer, and as most of you know, printing with photopolymers is a mess. So you can see there's some resin dripping off, but also what you'll notice is the front of each of those guards are fairly securely held to the build plate using these support structures, and especially for sports mouth guards, which need to be really impact absorbent, we're printing with elastomers. So the heavier and more viscous these resins get, the more you have to kind of support them just to make sure that you can get reliable prints. And then once you post-process and you do your IPA and your curing steps, we're then going to the same polishing step, and then you have your guard. What if we wanted to push this a little bit further and maybe explore other ways of using additive to improve this? So one way to do that is, again, start with a 3D file, but choose SLS or powder bed fusion instead. Again, the advantage here is, of course, there's no support materials because that's a self-supporting polymer cake that you're printing in. And once you have those parts, you can then post-process them. But again, today, the advantage of some of the technologies that we have at hand is just better solutions to post-process these thermoplastics. So instead of having to go the manual polishing route, which is just traditional buffing wheels most of the time, we can go the vapor smoothing route. Now, there's a couple of advantages to this. One is it's a repeatable and fairly measured process. We know exactly how long that process is going to take. And secondly, we're moving from single part flow to a batch. And again, for anything that's post-processing related beyond the printing step, it's just an advantage for speed as well as cost because it's reducing labor time. So batch processes are just generally preferable. And then once you have that, you have your final guard. So in this particular workflow, let's see what we can do with rethinking design for additive and how we can make the most of every step of the workflow on the production floor. So we start with a 3D file. And again, the advantages of additive and the design freedoms are, light weighting, reduced cost, or variable thicknesses. Again, this is something that you can only do if you're printing the final guard, because if you're thermoforming, you're dependent on the thickness of that blank that you use, and then depending on each patient's jaw and teeth, there's significant amount of thinning of that material. So that thinning can be anywhere from 15% to 40%, depending on how sharp some of these features are. And that's not just bad for reliability, but it's also just bad for the protection, which is really the primary function of this product. So we have the design freedoms of variable thickness, which is great for the clinician and the patient. But let's look at lightweighting. So one thing we can do is shell out this entire guard. So we just have a shell of a millimeter or two, and that reduces the amount of material that we use when we're printing. One disadvantage with this is we have a lot of powder that's not been solidified in the middle of that guard, and just generally less than ideal. So what can we do to get rid of that? Well, one thing is we can add some drain holes, similar to what we would do in photopolymer processes. We add some drain holes, and again, the advantage of adding drain holes at the posterior ends near your molars is it makes it easier across the production flow when you're trying to get rid of excess powder. All you need to do is put in a compressed air gun, and you kind of get rid of most of that. You don't really have to have a technician that kind of goes in manually and does too much of that. One thing that we're forgetting is for the vapor smoothing step, we're going to have to place them into the machine. And if we just place the guards on that tray that we saw, it's any part of that guard that's covered by the tray, or just not having equal exposure to that solvent is just not going to be smoothed as well. So the one solution is to add a sacrificial hook at the end of that guard. What that means is each of those hooks can just be lined up into the machine itself, and we're making sure that no part of the guard and the anatomy of the product itself is touching anything else, and so we're getting fairly even coverage of the solvent and the smoothing process. So that helps with post-processing. One thing that we're forgetting is traceability. So as one of the largest dental labs in the world, I think in a year across all of our product lines, we print more than 2 million individual parts. Whether they're the final product or whether they're something else like a dental model that the dentist requests. And so traceability is really important for us, and not just for the end of the process, but even in between steps, just for quality check and making sure that we know that the handshake between steps is happening, and we can measure the process and find out how long each of those steps are taking. So traceability, this is traditionally how it's done today. Any photopolymer printing that you see, this is pretty much how it's done. There's a tag in between the guard or the appliance, and generally speaking, that's kind of snapped off by a technician during that polishing step. And it's convenient because with photopolymers you can snap that off easily, but the disadvantage is the moment you snap that off, you want to do that before the curing step, because otherwise it's just harder to take off. And the moment you do that, you're then losing the tracking ID and the part itself. So it's just all kinds of confusion of which part corresponds to which part ID. And I have to say, when you're on a production floor and you see a few hundred of these, it's really hard to tell them apart. So traceability is something that we're missing. So how can we incorporate all of these into a solution that hopefully addresses each of these problems? So one possible solution is integrating that tracking ID into the sacrificial hook. So this solves a few different problems. It's solving the post-processing step in the fact that it's not covering any of the guard. So we know we're getting quality. It integrates the tracking ID into the part, but it's also attached to the part, and where it attaches to the part is not actually interfacing with the lips or the soft tissue of any of the patient. And again, this is a huge advantage because you'll know how sensitive your mouth is if you've ever felt a hair on your tongue or in your teeth. Human hair is between 50 and 100 microns, so it's really, really important to make sure that anything that touches anatomy is generally extremely clean and or just smooth. So this solves that problem. Solves the problem of just traceability, because the technician doesn't have to get rid of that until the very last step, which is the QC step. And again, because it's not making contact with any of the anatomy parts of the guard, that's just really easy to take off with a Dremel machining bit or just a cutting machine. And yeah, so that's just really one example that I wanted to touch on, but really the idea is to use this philosophy to move across the production floor and see how each of these can feed back into the design considerations for additive and not just the printing step. So we talked about design, perform and function. Pre-processing, again, with this particular example, we have the advantage of no support structures, so we don't really have to design for support removal. But again, designing for nesting efficiency, SLS, I think can get to about 25% reliably nesting efficiency. It's really hard to get reliable prints when you go beyond that. And in the previous slide, the kind of sacrificial hook that's sticking out, that's not great for efficiency. So one possible solution is to kind of curve that around the inside of the guard and just follow the function so that you're improving how many parts you can stack up in a build plate. Printing, again, designing for technology and material. The technology of choice was a deliberate one to take advantage of the fact that we can get rid of support structures and the fact that we can nest them more efficiently. And with the material, the advantage of using additive is that you can essentially, so if you're working with an elastomer TPU of, let's say 90A hardness, the shelling that you do of the guard itself and the wall thickness, you can just have a wide range of how that guard performs. You can get all the way down to 30 or 40A and just really even differentially adjust those thicknesses. So it might be the case that a clinician or an athlete prefers just a lot more firmness in certain parts of the guard, but not the others, and those are just design possibilities that are opened up now that just weren't there with the traditional thermoforming process. And with post-processing, again, we're designing for part handling because each of those hooks are used for the vapor smoothing step. But if we were to dye those parts, we're printing in white TPU, so if we were to dye those parts in any color, again, those are just hooks that can be used in the fixture that go into the dyeing tank, be removed, again, stays with the part ID, and doesn't have to affect the actual geometry or anatomy of the guard itself. We're designing for finishing and post-processing, so if in the future, if we're able to automate that polishing or finishing step, or if there's any other steps that are required based on specific notes from the dentist, that's something that we can take into account when we're going through this design process. And again, on the QC side of things, we're designing for traceability and just part flow in general across the board. And yeah, so really that was my goal, is just to say that we really should be expanding the scope of what we consider design for additive. And it's one of the things that will continue to push additive into high volume production, which for many of these use cases we sorely need it to be. Thank you.